Hello students, this is Mr. Hart. In this video we want to finish up talking about the life cycle of a star. Last time we talked about these two paths, how either a regular sized star will start to fuse hydrogen, and then when it can't fuse hydrogen it will fuse helium, then it will get rid of the excess material and turn into a white dwarf that just continues to glow from the excess heat. But if the star is really big, it will turn into a massive star. That massive star will turn into a red supergiant, which is fusing helium, and the leftover material goes supernova, which gives this massive explosion, and the leftover core turns into a neutron star or black hole. Okay, so let's talk about these two and what they mean specifically. What does it mean to become a neutron star, and what does it mean to become a black hole? Okay, so remember the white dwarf, how it's just not fusing anything. It's just so hot that it continues to glow. Well, neutron star and black hole are also similar, that they aren't fusing anything. They're just really heavy objects that are left over from the core of that star. Okay? But a neutron star is particularly interesting because what happens is once the star is too massive, okay, that core is too massive. Remember how we talked about how two hydrogen atoms don't want to be next to each other, right? They try to avoid each other, but if there's enough gravity, it pushes them together, okay, and they fuse. Well, once you have enough gravity, it gets even crazier because with an atom that has protons and electrons around the outside, there's so much gravity pushing in that it actually pushes the electrons into the protons and the neutrons, okay, and actually turns that proton into a neutron. A proton and electron turns into a neutron, okay? So we call that the electron degeneracy pressure, big fancy term. It basically just means instead of having an atom with proton, neutrons, lots of space, now suddenly your atom is the size of the proton and the neutron, okay? So instead of a big empty atom with lots of space, everything now gets compressed. So neutron stars are when this process has happened. There's so much gravity that there's no longer separate atoms. All the protons have been forced into the electrons, and now you just have a big, huge, dense star of neutrons. No protons, no electrons. All that space has been removed. So even though a neutron star might only be 12 miles in diameter, only 12 miles, that's tiny for a star, right? Its mass can be as large as 1.5 times our sun, okay? A neutron star is so heavy that if you took a teaspoon of it, okay, it would weigh 4 billion tons. Okay, it's just super dense because, again, instead of having those spacious atoms with electrons flowing around freely, now everything's been compressed, and so you have this super dense, super thick star. Okay, and that is what a neutron star has become. Okay, so that leftover core, right, still glows like a white dwarf, but it's super heavy and it's compressed everything down to the neutrons. Okay. Often you'll hear the term pulsar in astronomy. These things can actually be spinning really fast and have all sorts of weird magnetic effects. And so that actually will be like a little strobe light that constantly shoots out light at certain intervals. Okay, we call that a pulsar for the neutron stars spinning in a certain way. Okay, so that's what causes neutron stars. If you have even more gravity, then something really weird happens, and that's when the neutrons that are against each other and rubbing, now they even push into each other. The neutron degeneracy pressure disappears, okay? And that's when you're ripping fabric of space and all sorts of weird things, and that's when a black hole forms, okay? So there's so much gravity, it can't even hold particles. Particles can't even hold themselves apart from each other, okay? And that's why a black hole occurs. So, some fun things about a black hole. Again, the center of galaxies often have black holes because a lot of material has gathered into that spot from gravity to the center. And so that's why you often have a black hole near the center of a galaxy. The law students ask, well, how do we know a black hole is real, right? If you can't really see it, how do you know a black hole is even there, right? Or black holes even exist? Well, the fun thing is they've been a mathematical theory for a long time. But back in 2019, we actually took a picture of a black hole, okay? And if you want to understand what this picture is showing, I highly recommend a video by Veritasium on YouTube that goes through the details of what you're seeing. But basically what's happening is this black center is the black hole, and the lights you're seeing around the black hole is actually the material that's orbiting around the black hole. But because the black hole bends space around it, you can actually see things coming around the black hole to you, and that's all the light that you're seeing here. Okay, so things to the side of it, things below it, things above it, all that material bends around the black hole. The light bends around the black hole, and you can actually see it, and that's why you can see it in this picture. Okay, the other fun thing about this picture is how it was taken. Okay, usually for a telescope, for example, even the really big ones that Edwin Hubble used, you're limited by the size of the mirror or the lens you put in the telescope. Okay, so even if it's the size of, a building, you're still limited to the size of a building for magnification. Okay, but if you're trying to see something in the center of the galaxy, that's going to still be too small. So how they made this picture is they didn't use a single telescope. They actually used telescopes around the world to take this picture. Okay, and they used a lot of statistics. So maybe a couple telescopes could look in this area, and some could look in that area, and some could look in that area. Okay, over many years and many different times of the year, etc. Okay, and over time they were able to make the statistical calculations that generate this image. Okay, so it wasn't just one telescope; it was many telescopes, which essentially makes your effective telescope the size of the Earth, which is really cool. So an Earth-sized telescope is big enough to take a picture of a black hole. Okay. Other fun fact is that a lot of the telescopes they used were in remote areas in like South America and stuff. So they didn't have a strong enough internet connection to send the files over, especially since these were massive files they were using for these massive telescopes. Okay, so they actually had to mail hard drives with the pictures and everything to a central location to generate this image. So they snail mailed their information to each other. Okay, which is really funny to think about. Okay, but there you go. That's how we know black holes exist. We've now officially have taken a picture of them. Okay, back in 2019. Okay. And then we've had mathematical models for them for a long time. But again, it's just when you get enough mass gathered together that even particles cannot hold themselves apart from each other. Okay? And we won't talk about this in great detail, but there's all sorts of fun facts about black holes and what they do to you if you fall in. You get spaghettified and other fun things. One last thing I wanted to mention is if you've ever seen the movie Interstellar, they actually fly by a black hole and it kind of looks like this. Well, the fun thing is this was actually made with a simulation, and their simulation was so accurate that the people that made Interstellar actually were able to publish a paper about black holes because their mathematical calculations were so good. So this isn't just an artist's view of what a black hole might look like. They actually simulated what a black hole should look like, and it was so good they got a journal article out of it, which is really funny to think about, that a movie helped contribute to science, That's kind of cool if you think about it. All right, last thing we want to talk about is wormholes, and mostly just because a lot of people think black holes and wormholes are the same thing. They're actually not. They're slightly different. This picture, for example, is a artist's rendition of what a wormhole might look like. But a wormhole has a relatively simple construction. Okay, so let's say you had a really massive object like a black hole, okay, or a neutron star. Okay, I'm going to try and color it here. And let's say it's in this spot, okay, kind of in the center of this path right here. Well, black holes and massive objects bend the space around them, okay? So this space actually may get bent around this massive black hole or whatever it may be, okay? Well, if that object is massive enough, that space may bend enough that it goes back on itself, okay? So a wormhole occurs when space bends enough to intersect with itself again. Okay? Well, what does that do? It basically means you might be traveling along over here, and then suddenly you're over here because you went through the wormhole. Okay? Notice if you went along the regular path, it would have taken you a lot longer to get there. Okay, so a lot of people describe wormholes as portals or something like that. I want you to just think of them as space shortcuts. Okay, if you get enough space bending, you can take this shortcut from this location in space to that location in space. Okay, by going through the wormhole, but just caused by a massive bending of space. Okay, weird thing though is Einstein showed that space and time are connected, so it doesn't only bend space, it also bends time. So you might be traveling along in time and suddenly go through the wormhole, and now you're back to where you started. Okay, so you went back in time. For some other reasons, we don't think you can go forward in time, but we do believe if you went through a wormhole, you could go back in time. Okay, so a lot of movies play off of this. Wrinkle in Time, Deja Vu, etc. So you may have heard that as well. But again, it's just a space or time shortcut that you're taking. Okay, so that's a wormhole. We don't talk about them directly in our science, or I should say you don't need them per se for the unit we're talking about. But it's helpful to understand the difference between a black hole and a wormhole. A black hole can cause wormholes by bending the space around it. Okay? But there you go. Those are our three massive objects: neutron stars, black holes, and wormholes. Okay? So, hopefully that all made sense, and hopefully, again, just remembering that they're connected to the life cycle of a star. Okay? These massive objects can turn into neutron stars and black holes. Okay? Hopefully that made sense, and thank you for watching.